So this representation is all about laying the groundwork so that we can really start to explore how C types and pieces of data are actually laid out in the memory of the machine. So we're going to be going back and forth between the C abstractions, which we'll talk about in this presentation, and then in class we're going to be digging into the actual representation so that you can go back and forth between the machine representation and the C representation. Let's begin with a couple definitions specifically from the C language. So in C, an object is just a region of storage. So this has nothing to do with object orientation in case you've used other languages that talk about object orientation or object-oriented programming. So in C, an object is just a region of storage, and distinct objects never overlap. So each object has its own place in memory. That said, an object might have multiple names. We call those multiple names aliases. So how do you get aliases? That's where pointers come in, right? I can create an infinite number of pointers, all of which reference the same memory. And all of a sudden, all those pointers are the same names, are different names for the same object. So in the example here, we have one integer that we've allocated called foo, but I have two different pointers that are both pointers to integers. And then in the code snippet, I assign both of them to point to foo, right? And remember that ampersand says take the address of this variable. So at the end of that code snippet, both name1 and name2 reference the same memory. And so they are aliases for one another. We have just a couple more definitions. And the first one is definition. Talk about circularity. So in C, a definition does two things. It allocates an object and it creates a name for that object. So when you start writing your C programs and you specify your variables, things like int foo, char bar, etc., you are both saying, I want to allocate space for an integer, and I'm going to assign it the name foo. Now, why am I making a big deal about this? Because C also has the notion of something called a declaration. And a declaration is merely telling the compiler that there exists an object of some name and type, but it doesn't actually allocate space for it. So how do we do declarations that aren't definitions? Well, when we declare things as extern, what that says is somewhere someone is allocating space for an int. In this case, the int is called Erno. All I'm doing is telling you that it exists. And the reason we do that is so that in your code, you can refer to it, and the compiler is happy because you've told it that at some point it'll find out where that variable lives. And finally, when you put your program all together, you do the final linking phase. That's when we're going to try to find where that variable is and make the code reference it specifically. The other place that we use declarations a lot is when we declare functions. So a lot of times in an H file, we'll say, here are all the functions that this library talks about. We're not going to define all the functions, we're just going to tell you they exist. And that's what lets you compile an individual program, an individual file that may not be a complete program that references other functions from libraries or from other files that you've written. So a declaration doesn't actually allocate space for the object, it simply tells the compiler about the existence of the object. When you define it, that's when you actually allocate space for it. So given that, a reasonable question to ask is, how many times can I define something and how many times can I declare it? Well, since the definition actually allocates space for it, you should only do that once. So for any particular variable, there should be a single definition, but you might have multiple declarations. So for example, Erno is a great example. It gets defined only once, but any file that refers to Erno will have a declaration for it, primarily an extern, so that the compiler knows that the variable is going to exist and you can refer to it and treat it as an integer. In addition to a name and a type, every object in C also has a size. And you can find out what that size is by using the size of operator. So if you look at these two examples, in the first one we're doing a printf and we're saying an integer has size, and then we're saying tell me the size of an int. You can also declare a variable of type int and say an integer has a size and then print out the size of that particular variable. So you can use sizeOn with either a specific type or a variable of a specific type. Notice the format here. I'm using %ZU. Now what does that mean? Well, the U means unsigned, and the Z means that the type of the value I'm printing out is actually a type called a size T. So sizeOf returns an unsigned value called a size T. And what it's going to tell you when you ask about the size is it's actually the number of bytes. Okay? And now the size of the object is actually going to determine the values that it can store. So an integer with 4 bytes can store up to 2 to the 32 different values, or about 4 billion. But let's take a smaller object that we can wrap our heads around a little bit better. So a character is 8 bits, and so the maximum value it can contain is 255. And if you don't know why that's true, go back and look at the video on hexadecimal and binary. Now I said that a size T is an unsigned type, and that's correct. There's another type called a signed size T, or S size T, and that is a signed size T. And you might say, but wait a minute, how can a size be negative? Like, you can't have a negative number of bytes, and that's true. But if what you're trying to do is return a size from a function, and you want to be able to return an error condition, sometimes called an out-of-band value, then frequently the way we do that is by saying -1. And so if you want to return this out-of-band value, you can use an S size T, which will let you return the -1. Now C has 2 different kinds of types. There are fundamental types that are built into the language. And then there are derived types that programmers construct out of fundamental types or other derived types. So you've seen most of these before. We have integers and unsigned integers, we have longs and unsigned longs, we have shorts, we have characters, we have floating point representations, both float and double. These are the types that are built into the language. Perhaps more interesting, though, we have derived types as well. Derived types are composed of fundamental types or other derived types, and there are primarily 3 different ways that we can construct more complex types. I'm guessing that you've all seen arrays, which are a collection of contiguously allocated objects of the same type. We'll talk about that in a minute. Then there are structs, which let you take a collection of fields potentially of different types and bundle them together. And then we have unions, which are a way of storing different data types in the same memory locations. Now at first blush, unions may seem to contradict what I said about each object has its own distinct space, but a union is an intentional construct that says I have one object, so there's one chunk of space, but depending on how I access it, I might want to think of it differently. So I'll go into each of these in a little bit more detail. I'm guessing that most of you who've programmed in C have used arrays before. So we define arrays by using the square brackets and specifying a size. So in the example here, we have a character array of 10 bytes, 10 characters. We have an integer array of 52 integers. On our machine, an integer is how many bytes? That's right, it's 4 bytes. So this is declaring an object whose size is actually 208 bytes long, but we're accessing it as 52 integers, all allocated contiguously. And this idea that array elements are allocated contiguously is really central to memory management in C, and you'll be doing some exercises in class to play with that. The other thing that's important about arrays is that they're all the same type. So that's how you define them, and then the way we access them also uses the square brackets. Indexing starts at 0, and you can either read a value out of an array by saying C array sub 3, or you can assign a value to the array. And as I said, we'll get some practice with this in class. Let's talk about structs next. So if you've programmed in a language with records or classes, this might feel familiar. If you haven't programmed in those languages, don't worry about it. A struct, which is short for structure, is a way of packaging a bunch of related fields together so that you can access them as a single entity. So let's imagine that I'm building a graphics package and I want to represent points in 3-space. I might construct a struct of type point, which would have 3 fields, each of which represents the x, the y, and the z coordinate. So that's how I would do it here. This is a declaration, and it says, compiler, I want you to know that I have these things called struct points, and they contain 3 integer fields. I've not allocated any space for one, but I'm telling the compiler that this is a new type. It's a derived type that's going to exist in this file. Alternately, on the right-hand side, let's imagine I'm building a database of Harvard students. So I might want to know your name, and I'm going to allocate 20 characters for that. Perhaps I want your age, an unsigned integer, and then I want to know your house affiliation. So I have another character array. So both of these are declarations. If I now want to create some variables that are of this derived type, I do that as below. So I can say struct point p, and that allocates space for one of these point structures, or struct student Margot allocates space for one of these student structures. So let's go into this in a little more detail. On the last slide, I separated the definition and the declaration of the variables, but frequently you will see them combined. So I have the same 2 structures I had on the last slide, but now I'm combining the definition and the declaration. So I'm saying, I'd like to create this thing called a struct point. It has these 3 integer fields, and I'm going to allocate a variable of that type and name it p. So that's a definition of the variable. Similarly, here's my student structure, and instead of defining the Margot variable separately, I'll do it the same place where I declare the student structure. Frequently, when we use structures, we actually will use them in conjunction with type defs. So type defs you can think of as really a way of creating new types that you can use in your program. And so the format of a type def is that you say, type def, here's a type, a definition of a type or a declaration of a type, and I'm going to give it a name. So in these 2 examples, what I'm now saying is, okay, I'm going to create a name for a type. So I say type def. The type I'm creating is a struct with these 3 fields, and I'm now going to give it the type name of point. So you can think of it as really creating a type. And so when I say point p now, that says that p is a variable. I've allocated space for it. The name is p, and its type is one of these structures. Similarly, on the right-hand side, I've done the same thing. I'm saying, here's my student structure, but what I'm doing is I'm saying, make a new type for it and call it student. And once I've done that, now I can allocate a variable named Margot of type student. So type defs are a way to give names to these types, and frequently that's the convenient way that we do structures. Finally, our third derived type is a union. Unions are used most frequently when you have an object that you want to reference in different ways. So what do I mean by that? Let's imagine that I've got 4 bytes, and sometimes I want to access those 4 bytes as a single integer, but sometimes I want to access them as 2 16-bit integers, or 2 shorts, and sometimes I want to access those 32 bytes as 4 characters. I can do that by creating a union that gives different names to those different representations. So the syntax of a union looks a lot like a struct. So instead of saying struct, I give it the keyword union. I can refer to the name of the union I have here. So this is a data union. And now I have 3 different representations of the same space. So I might have an integer value, or I might have 2 shorts. Well, those are 2 values, so I'm going to wrap those in a structure. Okay, so notice that I say struct, it's got these 2 short values, and it's got the name sval, so I've really allocated the space for it. Or here's another structure that's going to have 4 character variables. And so there's 4 bytes allocated here, And depending on which of these fields I use, so when I use this one, I'm talking about all of these, whereas sval1 is going to point to the 2 bytes, sval2 is going to point to these 2 bytes, okay? And then the characters are going to each point to a single byte. So at different points in the program, I might use different parts of the union to describe this data. Now that we've learned how to declare structs and unions, we really ought to figure out how to access the different fields in them. And this is where we use the dot operator. So imagine that we have the student structure Margot, and then we have the union data U. Now let's imagine we want to access some of the fields. So if I want to grab the name out of the Margot structure, I say Margot.name. If I have a pointer to the structure instead of the structure itself, then I use the arrow to dereference. And the same holds true with union. So if I have a union, u.intval grabs me the integer value. Now u.cval gives me the structure that are the character values, and if I want a particular character in there, then it's u.cval.cval1. Okay, and if I had a pointer to this union, I would use u deref, so u arrow cval, but then that would still give me an entire structure, and that structure is always in the union, so then I would use the dot. So dots are when you have the structure itself, arrows are when you have a pointer to the structure. Last thing I want to talk about in this presentation is pointer arithmetic, and this is something that we'll spend a lot more time on in class, but I want to have a quick review here, because in some ways the combination of pointers, types, and arrays in C, it's kind of magical. So the key idea is that if we have a pointer of type T, and that pointer is P, then there's 2 different ways that we can access elements in an array. There's the standard way, p sub I, and if I want the address of that location where the ith element of array is, I would say the address of p sub I. So that's this syntax here. But it turns out that the address p sub I is actually exactly the same as adding I to p. And so independent of what the type is, the compiler looks at the type of p and it knows how much to increment if you want to get to the ith element. So these 2 are identical, and by corollary, the pointer p is exactly the same as the address of p sub 0. So let's look at a couple examples here. If we have an integer pointer and I malloc some memory, this is dynamically allocated memory, and I'm saying I want 10 things, each of which is the size of an int. So in this case, I'm going to allocate 40 bytes. Okay. Then here are just some statements that we know to be true. So whatever IP got assigned to is exactly the same as the address of the 0th element of the array I just allocated. Similarly, the address of the 4th element, so this one, right, is IP plus 4. Because even though we're only adding 4, the compiler sees that that's an integer pointer, and it's going to actually add 16 to the address to give us the address. And again, you'll get practice looking at this in class. And I can get the contents of the array the same way that I say IP sub 6. IP plus 6 generates the address of an element, and I can use the star operator to take the contents of it. So these are the basics. We'll do a little bit more, and then we'll do a quick practice, and then you'll be ready to do the exercises in class. So remember that a pointer is merely an address. Okay, so let's imagine that we have a pointer p, and its value, that is the address that p contains, is this 32-bit number. If p is of type int star, that is, it's a pointer to an integer, then just like we saw on the last slide, the address of p sub 0 is exactly the same as p, so these two are equal. The address of p sub 1, however, is not 1 greater than that, it's 4 greater than that. And the reason is that an integer is 4 bytes. And so similarly, when I say p plus 1, the compiler says, p is an integer. I'm sorry, p is a pointer to an integer. Integers are 4 bytes. So when you say p plus 1, I should take the address and I should add 4. And that's why these things are actually the same. So let's step through a practice problem, and then the web work will give you an opportunity for some similar problems. So let's again assign a value to p, which is an address. This time, let's assume that p is a pointer to a character. If p is a pointer to a character, and I say p plus 5, what does that actually mean? Well, what it means is we're going to add 5 times however large the objects are to which p points. Well, p points to a character. Characters are 1 byte. So in this case, we actually get sort of the number we might expect, which is 5 greater than p. But now, let's say that p is a long. Okay, a long is 8 bytes. So now, when I say what's p plus 2, what are you going to be? You have two choices. Is it 0x80481002, or is it 0x80481010? Well, if p were still a character, this would be right, but p is not. P is a long, which is 8 bytes. So if we're going to add 2 of those, that's 16 bytes. 16 in hex is 10. Okay? So if p is defined to be a pointer to some type, okay, so that's, some generic type, and the size of that type is 16, then what's the value of p plus 1? Well, the value of p plus 1 is basically going to equal the value of p as a plain number plus the size of t. So it's actually going to be exactly the number we got before, which is 80481010. So pointer arithmetic, instead of just adding that value, it's that value times the size of the type that the pointer is referencing.